In this lesson, we're going to learn about the complex number system and imaginary numbers. Let's start by looking at this problem. Does this problem have a solution?
Well, let's think about it. Is there any number you could plug in for x such that when you square it, you get -1? There is no solution to this problem, and that's because whenever you square a number, you always end up with a positive answer, so it's impossible to square a number and get -1. Notice I put here no real solution because there is no solution in the real number system.
And just a reminder, real numbers are all of the types of numbers we've seen so far. Real numbers include whole numbers, integers, fractions, decimals, and even irrational numbers like pi. Problems like problem number 1 that you see here come up a lot in math and science. So mathematicians decided that we needed a way to deal with problems like these.
So mathematicians decided we're going to define a number such that when you square it, you get -1. And mathematicians said we're defining a number I. And I is a number such that when you square it, we get -1. By defining the imaginary number I, mathematicians opened up a whole lot of mathematical problems that could now be solved. A question that you might ask next is, if I squared is -1, what is I? Well, we can answer this question just by using the mathematics that we've learned so far. So let's start off with the fact that we know that I squared is equal to -1. Let's take the square root of both sides. The square root and the square are inverse operations. They cancel each other out. So the square root of I squared is just I. And so we're left with I is equal to the square root of -1. So we can enter that right here. I is equal to the square root of -1. And I've highlighted this box here because the information in this box is going to be very important. Whenever we see I squared, there's a much simpler way to write it, and that's -1. I squared is equal to -1. So in mathematics, whenever we see I squared, we replace it with -1. So if you're working through a problem and you get to some point where you see I squared, go ahead and replace it with -1. In addition, if you're working through a problem and you come across the square root of -1, we learned back in chapter 6, section 1, that you cannot take the square root of negative numbers. There's no real solution. And this is not a real number, it's an imaginary number, and it's defined as the imaginary number I. So we like to label this as an imaginary number, and so if we see this in a mathematics problem, we always replace it with I.
And I love this quote that I put up here. Ask any physical scientist or engineer how they would get on without using the square root of -1. They will tell you most of our technology depends on it.
If you look back at your chapter 6, section 1 notes, you'll see problems like this. The index is an implied 2 here. We said when the index is even, we're not allowed to have negative numbers underneath the square root. If that did happen, we wrote that there is no real solution.
But the square root of negative numbers comes up a lot in math, science, engineering, and computer science. So mathematicians needed a way to perform calculations on square roots of negative numbers.
So I was invented so that people can perform calculations involving the square roots of negative numbers. So there are two types of numbers. There are real numbers, which are all of the numbers we've seen up until today, and then there are imaginary numbers. Imaginary numbers are square roots of negative numbers, and the imaginary number I is defined as the square root of -1.
Complex numbers is a big umbrella term. Complex numbers include all real numbers and all imaginary numbers. And as you see here, the term complex numbers includes three types of numbers: real numbers, pure imaginary numbers, and numbers that contain a real term and an imaginary term. Here are some examples of real numbers. Remember, real numbers are all of the numbers we've studied in class so far, including whole numbers, integers, decimals, fractions, rational numbers, and irrational numbers.
The term complex numbers also includes what we call pure imaginary numbers. So here's some examples of pure imaginary numbers.
I is a pure imaginary number, and any number involving I with a coefficient attached to it is also called a pure imaginary number.
Complex numbers also include numbers that are a combination of both real and pure imaginary numbers. So here's a number that has a real part and an imaginary part. So this number is not a real number, it's not a pure imaginary number, it's a combination of the two. But it still falls under the category of a complex number.
Here's one last example of a number that contains a real term and an imaginary term. So anytime we have a square root of a negative number, that is an imaginary number. And we always like to rewrite square roots of negative numbers in the pure imaginary number form. Remember, as we wrote on the previous page, a pure imaginary number will involve I and a coefficient attached to it.
Anytime you see the square root of a negative number, you can rewrite it as a pure imaginary number using I. The first step is we're going to rewrite this negative number as a positive number times negative 1. So we're going to rewrite negative 25 as positive 25 times negative 1. Now we know the product property of radicals says when you multiply two quantities underneath a radical, you can break that apart into two separate radicals. So let's do that, and let's write this as the square root of 25 times the square root of negative 1. Now we just need to simplify, and then we'll be finished. The square root of 25 simplifies to 5.
And remember what we wrote and highlighted on the first page. Anytime in a math problem, if you see the square root of negative 1, replace it with I.
So I see the square root of negative 1 right here, so I'm going to replace it with I. Now we've written this square root of a negative number in the pure imaginary number form with I and a coefficient. Let's take a look at the next example. So we see that we have a square root of a negative number, so this is an imaginary number, and we'd like to rewrite it using I. First step, rewrite negative 14 as 14 times negative 1. Then we break this apart into two separate radicals, and then we simplify each radical. The square root of 14 cannot be simplified. There are no perfect squares that multiply into 14, so we'll leave this as the square root of 14. Anytime in any mathematics problem, if we see the square root of negative 1, we replace it with I. So we'll replace the square root of negative 1 with I. And I just want to talk about the way we write this final answer. When you write your final answer, if you're dealing with a pure imaginary number, standard form says put the coefficient first and then put the I last. So this is considered standard form. Now be very careful. In the problems that you will see, I should never be underneath the radical. A very common student mistake is to write their final answer like this. I should never be underneath the radical. Because of this, and because sometimes students get sloppy and they'll be writing their final answer real quickly like this, and it'll be hard to tell if they accidentally put I underneath the radical or if they intended for I to be outside of the radical. Because of that, some teachers like to put the I out front and to write their final answer like this. Either one of these will be accepted unless the problem specifically asks for standard form. If the problem specifically asks for standard form, you want to write your answer like this. Let's take a look at problem number 4. For problem number 4, we have a negative out front. I'm just going to take that negative and move it to the side for now, and I reroute the negative as a negative 1 times. Now, we see that we're dealing with the square root of a negative number. Anytime we have the square root of a negative number, that means we're dealing with an imaginary number, and we like to write imaginary numbers in pure imaginary form using I. The first step of that process is we're going to rewrite negative 48 as 48 times negative 1. Then we can pull this apart into two separate radicals, and then we'll simplify each radical separately. To simplify the square root of 48, let's ask ourselves, what is the largest perfect square that multiplies into 48? You'll find that the largest perfect square that multiplies into 48 is 16. So let's rewrite 48 as 16 times 3. And whenever we see the square root of negative 1, we're replacing it with I. Now let's proceed to simplify this radical. 16 is a perfect square, so let's write it as 4 squared. Then we can pull the 4 out of the radical. And then we can go ahead and multiply the coefficients. Negative 1 times 4 will give us a negative 4, radical 3i. And this is our final answer. Again, make sure not to put the I underneath the radical. And this is considered standard form. If your problem does not specify standard form, then if you'd like, you can move the I out front and write your final answer like this.
Let's quickly review standard form For problems involving imaginary numbers, here are some examples of pure imaginary numbers written in standard form. For pure imaginary numbers, standard form means that you've written the coefficient first and I last.
And make sure your I is never underneath the radical. Next, we're going to look at those types of numbers that have a real term and an imaginary term. So standard form for those types of numbers looks like this. When you're dealing with these numbers that have a real part and an imaginary part, if you're asked to write those answers in standard form, make sure that you put the real part first, and then always put the imaginary part second, just like it's written here. And again, for the imaginary part, you should put the coefficient first and the I second.
And here are some other examples of standard form for expressions involving a real part and an imaginary part.
Again, standard form for these types of numbers means you always put the real number first and the imaginary part second. So here we're looking at those types of numbers that have a real part and also an imaginary part, and we're asked to write them in standard form.
And if you're supposed to write your answers in standard form, the instructions will often ask you to write your answers in the form A plus BI. This just means standard form, where A is the real part and BI is the imaginary part.
For this first example here, to write this in standard form, to start, notice that we have an imaginary number here. And in standard form, imaginary numbers should always be written in terms of I. So let's start by rewriting this using I. To start, we have to rewrite the negative 16 as 16 times negative 1. Now we can break this apart into two separate radicals, and now let's simplify. The square root of 16 will simplify to 4. Again, anytime we see the square root of negative 1, we always replace it with I. And here's our final answer. Let's just double check that we've written it in standard form. For standard form, we always put the real part first, and we've done that here, and then we always put the imaginary part second. And for the imaginary part, we have the coefficient first and the I last. So this is written successfully in standard form. Let's try the next problem together. So to write this in standard form, we want to start by rewriting this imaginary number using I. So we'll start by rewriting negative 135 as 135 times negative 1. Now we can break apart this radical into two separate radicals. Now, 135 is not a perfect square, so we need to find the largest perfect square that multiplies into 135. And if you look at your list of perfect squares, you'll find that 9 is the largest perfect square that multiplies into 135. So let's rewrite 135 as 9 times 15. Then anytime we see the square root of negative 1, we always replace it with I. And 9 is a perfect square, so let's go ahead and rewrite 9 as 3 squared. And then we can pull the 3 out of the radical. And this is written in standard form. We've got the real part written first and the imaginary part written second. Make sure your I is not underneath your radical symbol. Now be careful here. A lot of people will try to simplify this further by adding the 5 and the 3 together. You don't want to do that. You also don't want to combine 3 minus 4 here either. Let's look at that real quickly on the next page. If we solve this problem here, we know that these are not like terms, so we wouldn't combine the 3 minus 4. It works the same way if you have this problem. These numbers are not like terms, so we do not want to combine the 3 minus 4. Similarly, if we saw a problem like this, these are not like terms, so we wouldn't try to combine them. The final answer we got in our last problem looked like this. These are not like terms because they don't have the same variable base. This has a variable base of x, and this has no variable base at all, so they're not like terms. Same thing here. These are not like terms because they don't have the same radical base. This 3 is attached to the square root of 15i. This 5 has no radical base. So the 5 and the 3 do not have the same base. They're not like radicals. We cannot combine them. Let's take a look at a couple more examples. Again, you're asked to write your answer in standard form, and some textbooks refer to standard form as A plus BI, where A represents the real part and BI represents the imaginary part. So we're asked to multiply. So here let's go ahead and distribute. And I want to compare this to a related problem. All I did here was I replaced the I with an x. And if we were to distribute here, we would get 12x minus 24x squared. Now, variables are quantities that can vary, so x can be whatever we define it to be. I is not a variable. It doesn't vary. I is the square root of -1 always. So I is not a variable, but the way it works mathematically is very similar to the way a variable works. So we can distribute here just like we distributed over here. 6i times 2 will give us 12i, and 6i times -4i will give us -24i squared. Now the big difference happens next, because with this problem, you are finished here. Maybe you want to put the variables in descending order and write it like this, so that the exponents are written in descending order, but there's no further simplification we can do here. For problems involving I, we need to further simplify this. Let's look back to the first page of our worksheet. On the first page of our worksheet, we had this highlighted box, and we said if you ever see the square root of -1, we always replace it with I. We've seen several problems where we've used that, but the other important piece of information here is whenever you see I squared, we're always going to replace it with -1. Remember, mathematicians defined I squared as being equal to -1. So in any math problem, if you see I squared, there's a much simpler way to write it. We can always write it as -1. So here we see I squared, so let's go ahead and replace that I squared with -1. And then we can simplify this to 12i, and -24 times -1 will give us a +24. Now our answer is simplified as it can get, but it's not quite written in standard form, because remember, for standard form, we're supposed to put the real part first. So let's put the 24 first, and then we're supposed to put the imaginary part second. So we'll put the +12i second. Now, notice, because this often causes confusion, in your final answer, you can have I. There is no simpler way to write I, so I is fine to have in your final answer. But in your final answer, you should never have I squared, because there's a much simpler way to write I squared. I squared is just equal to -1. So for your final answer, you should never see I squared. You should always replace it with -1. But I in your final answer is just fine. Let's go ahead and take a look at this problem, and we want to FOIL here. So to FOIL, we'll multiply the first. 2 times 4 will give us 8. Then we'll do the outer. 2 times a +3i will give us a +6i. Then we'll do the inner. I times 4 will give us a +4i. And then we'll do the last. I times 3i will give us a +3i squared. These are like terms, so let's go ahead and combine those to get 8 plus 10i plus 3i squared. Now, remember, I is just fine to have in your final answer, but you should never have I squared, because there's a much simpler way to write I squared. I squared is equal to -1. So let's go ahead and replace I squared with -1. And now we can simplify. 3 times -1 will give us a -3, and then we can combine the 8 minus 3 to give us 5. And just to double check, this is in standard form. We have the real part written first and the imaginary part written second. Let's take a look at this problem here. Now, off to the side real quick, I want to show the most common incorrect way that this problem is solved. People will try to distribute the exponent to give you 2 squared minus 7i squared. But exponents do not distribute across addition or subtraction like that, so this is incorrect. The correct way to solve this is to rewrite this and then FOIL. So we'll rewrite this as 2 minus 7i times 2 minus 7i. Then we can go ahead and FOIL. And when we're FOILing, we'll multiply the first. 2 times 2 will give us 4. Then we'll do the outer. 2 times -7i will give us a -14i. Then we'll do the inner. -7i times 2 will give us another -14i. And then we'll do the last. -7i times -7i will give us a +49i squared. Now let's see, these are like terms, so let's combine those. -14i minus 14i will give us a -28i. Now remember, having I in your final answer is just fine, because there's no simpler way to write I. But we never want I squared in our final answer, because there's a much simpler way to write I squared. I squared should always be rewritten or replaced with -1. And then 49 times -1 will give us a -49. And then if we combine 4 minus 49 will give us negative 45. And just to double check that this is written in standard form, we've got the real part written first and the imaginary part written second. Next, we're going to talk about complex conjugates. Now remember, to find a conjugate, all you have to do is change the sign in the middle. So since this is a subtraction sign, we change it to an addition sign. And now we found the conjugate. These two are conjugates because they look identical, but the signs in the middle are opposite. To find the conjugate of this expression, we just change the sign in the middle. Lastly, to find this conjugate, we just change the sign in the middle again. So this example here, these are conjugates because they look identical, but one has a plus sign in the middle and the other has a subtraction sign in the middle. Now, just a quick review of conjugates. You can have problems involving complex conjugates. These are conjugates since they look identical, but the signs in the middle are opposite. They're called complex conjugates since they involve the imaginary number I. You could have problems involving conjugates that contain radicals, for example. These are conjugates since they look almost identical. The only difference is the sign in the middle are opposite. Or you could have more simpler expressions that are conjugates, such as. Now, when you're multiplying conjugates, you can always FOIL, or whenever you're multiplying conjugates, you can also use the difference of two squares formula. So we'll take a look at those two approaches in the context of complex conjugates like we have here. So these are complex conjugates. So to multiply these, we can either FOIL or we can use the difference of two squares formula. Let's FOIL first. If we FOIL, we multiply the first. Negative 2 times negative 2 will give us positive 4. Then we do the outer. Negative 2 times negative 5i will give us a positive 10i. Then we do the inner. 5i times negative 2 will give us negative 10i. And then we do the last. Positive 5i times negative 5i will give us a negative 25i squared. Now, whenever you're foiling conjugates, whether you're foiling complex conjugates or conjugates involving radicals or conjugates that look like these, whenever you foil, the middle terms will always cancel out. And that's exactly what happens here. So we're just left with 4 minus 25i squared. Now remember, we should never have I squared in our final answer because there's a much simpler way to write it. I squared should always be rewritten as negative 1. And this can now simplify to 4 plus 25, which leaves us with a final answer of 29. Now again, whenever you're multiplying conjugates, you can always FOIL, or you can use the difference of two squares formula. Let's take a quick look at a simpler example to review the difference of two squares formula. So these are all conjugates, and anytime you're multiplying conjugates, you can use the difference of two squares formula. Let's apply that formula to this bottom problem here. So the difference of two squares formula tells us we take the first piece here and square it to get x squared. Then we take the second piece here and square it to get 4 squared. And then we put a minus sign in the middle. This is why it's called the difference of two squares formula, because you're taking the difference of two squares. And this would simplify to x squared minus 16. Let's use the same approach on the complex conjugate problem we were just working on. I'm just going to start by rewriting this original problem. Again, anytime you have conjugates, you can always use the difference of two squares formula. And that formula tells you to take the first quantity and square it, which gives us negative 2 squared. Then we take the second quantity and square it to get 5i squared. And then we always put a minus sign in the middle. And let's simplify. Negative 2 squared will give us a positive 4. And 5i squared, if we square the 5, that'll give us 25. And if we square the I, that'll give us I squared. And just like we did over here, we can replace the I squared with negative 1 and simplify from there. And we get the same answer whether we FOIL or use the difference of two squares formula. Now, before we complete these last two problems, I want to quickly look back. In Chapter 6, Section 3, we learned the product property. And the product property told us that if you're multiplying two radicals, as long as they have the same index, you can combine that multiplication underneath one radical symbol. Notice here, though, it says that the product property works when the radicals are real numbers. And that's what we're going to discuss here. The product property of radicals cannot be used when multiplying two square roots of negative numbers. For example, here, you're multiplying two square roots of negative numbers. The product property will give us the wrong answer. So I did the best drawing of a stop sign that I could do here because I want to illustrate the wrong way to solve this. Don't use the product property. The product property says when you're multiplying square roots to combine that multiplication underneath one square root symbol, like this. If we did this, negative 64 times negative 4 gives us a positive 256, and the square root of 256 gives us 16. This is not the correct answer. The product property of radicals will not give you the correct answer when you're multiplying the square root of a negative number times the square root of a negative number. The correct way to solve this is to first rewrite both radicals using I. So I'm going to start by copying down the original problem, and I'm going to rewrite both of these using I. First step was to rewrite negative 64 as 64 times negative 1, and to rewrite negative 4 as 4 times negative 1. Next step, we'll break apart the radicals, and then we'll simplify. The square root of 64 gives us 8. Anytime we see the square root of negative 1, we replace it with I. The square root of 4 gives us 2, and then we see the square root of negative 1, so we'll replace it with I. So we've completed step 1. We've rewritten using I. Next step is to multiply and simplify. And to multiply, we multiply the coefficients. 8 times 2 will give us 16. And we multiply the i's. I times I will give us I squared. Now remember, we never like to have I squared in our final answer. We always replace it with negative 1. And this will leave us with a final answer of negative 16. So the product property of radicals almost gave us the correct answer, but it wasn't quite correct. It gave us positive 16. The actual correct answer is negative 16. Let's take a look at the last example here. This is a problem where we're going to FOIL, but when we FOIL, we're going to run into an issue. When we do the last, we're going to be multiplying the square root of a negative number times the square root of a negative number. And when we do that, we cannot use the product property of radicals. Instead of using the product property of radicals, we want to rewrite using I as our first step, just like we did over here. So I'm going to focus on these two square roots of negative numbers and rewrite them using I. First, I rewrote negative 36 as 36 times negative 1, and I rewrote negative 9 as 9 times negative 1. Next, let's pull this apart into two separate radicals. Now let's simplify those radicals. Square root of 36 simplifies to 6. Anytime we see the square root of negative 1, we replace it with I. Square root of 9 simplifies to 3, and the square root of negative 1 is always rewritten as I. Now we've completed the first step. We've rewritten using I. Now we can go ahead and FOIL and simplify. And I've started by just copying down the exact expression that we left off with. Now we can go ahead and FOIL. If we multiply the first, 2 times 4 will give us 8. Then we can multiply the outer. 2 times negative 3i will give us negative 6i. Then we'll do the inner. 6i times 4 will give us a positive 24i. And 6i times negative 3i will give us negative 18i squared. These are like terms, so let's combine them. Negative 6i plus 24i gave us 18i. And then again in our final answer, we're okay with having I, but we never want I squared in our final answer because there's a much simpler way to write I squared. We always rewrite I squared as negative 1. And then negative 18 times negative 1 simplifies to a positive 18. And then we can combine the 8 plus the 18 to give us 26 plus 18i. And the problem specifies that we want standard form, so we make sure that we put the real part first, which we did, and the imaginary part second.